This is chemistry, energy. Here we'll look at heat flow. So heat is energy that is transferred from one object to another because of a difference in their temperature. Heat flow accompanies all physical and chemical processes that occur within the universe, and it usually travels from a hot system to a cold system. And I'll give an example of this in just a second. I just want to make sure you are comfortable with some of this terminology. So we have two parts to the universe in chemistry. This is not the overall universe, right? We're not studying the solar system, anything like that. But our universe in chemistry involves what's called a system, which is the part of the universe that we focus on or study like an experiment, and the surroundings. The rest of the universe that interacts with that system. And it looks a little something like this. But I thought I'd give you a little more concrete example. Let's say you had dinner, right? And you have some leftovers. So you want to preserve your dinner. I can get this here. So where's the dinner going to go? In your fridge. So what eventually happens to the dinner that's left over? You're going to put it in the fridge, and this dinner will be preserved because its temperature is going to be reduced, right? But what's actually happening to the dinner, it's not getting colder. That's what most people think is happening. And yeah, I guess you could think that way because it feels cold to the touch, right? But what's actually happening to the dinner is that it is losing heat to its surroundings. Its surroundings have a reduced temperature, right? So what did I just say here? What's the direction of heat flow, right? From hot to cold. So your dinner was hot, and the fridge has the colder temperature, right? So this heat is being lost. It's losing heat to the refrigerator, right? So that's how I want you to think of heat flow, right? So what did it say up here? It accompanies all physical and chemical processes, usually travels from a hot system to a cold system. So the hot system was the dinner, the cold system was the fridge, so the dinner is losing heat to its surroundings. Okay? All right, so there is a direction of heat flow, right? Our heat flow actually is going to be a calculation, something we can actually calculate using numbers. And there's a new letter for you, it's called Q, probably because a lot of other letters were being used up. So Q represents heat flowing into or out of a system. Now when Q is positive, you can come up with a positive calculation. This is when energy is flowing from the surroundings to the system. And this is called endothermic. So there's a couple different ways to look at this. So you could say that the surroundings feel cold. Good example is an ice pack. Like those ones that you have to step on or squeeze, right, and they feel cold to the touch. What's actually happening in there is that there are two liquid packets, and if the seal is broken and those two chemicals mix, they will mix in such a way that they will take in energy and feel cold to us. So that is endothermic. So energy is flowing from the surroundings to that system of those two chemicals. They interact and feel cold to us. Now, it's not always an accompaniment of feeling cold, right? That's just a good example of you understanding that energy is going into the system. We do also have some phase changes that involve endothermic processes. So melting, right, is solid to liquid. So in order for that solid to become a liquid, like butter, right? If you melt butter in a pan, in order to cook with it, it eventually becomes liquid, right? What did the butter have to do in order to melt? It had to take in energy from the surroundings. Now, does this feel cold? No. But what happened, right? It had to take in that energy in order to change its phase. That is endothermic. Evaporating is what? Liquid to gas. So in order for that liquid to become a gas, right, to change that phase, that liquid had to take in energy in order to become a gas. Now, did you feel something cold here? No, liquid to gas is usually at a higher temperature, right? So you just have to understand it's the direction of that energy or heat flow. So these are endothermic phase changes. They don't necessarily feel cold, right? This is a reaction that happened to feel cold, but this is a phase change, not necessarily feeling cold, but how did that change actually occur? Energy had to go into the system. Now, the opposite, when Q is negative with your calculation, right? This is when heat flows from the system to the surroundings. And this is called exothermic. And yes, one example could be a hand warmer, right? So this is a reaction where the surroundings to us would feel warm. That's a chemical reaction. So what's actually happening in that hand warmer? Same concept as the cold pack. When two liquids meet, right? When they meet and become warm, they release their energies flowing from the system to the surroundings, and we feel that heat energy, right? So that's exothermic. But now in terms of a phase change, right? This doesn't necessarily have to involve a rise in temperature. So what is condensation, right? It's actually the opposite of evaporating. This is a gas going to a liquid. So that gas has to do what in order to become a liquid? It has to release its energy to go back to a liquid phase. Does that feel warm? No, because actually phase changes don't involve a temperature change. We learned that in the last unit with the heating and cooling curves, right? It's that flat line. So during this time, it isn't going to feel warm to us, right? But it's the gas molecules releasing that energy to the surroundings in order to go back to the liquid phase. Freezing, same thing, it's the opposite of melting, right? You have a liquid that's trying to become a solid. It has to release that energy to the surroundings and become the solid. Does it necessarily feel warm to us? No, right? That's a reaction that feels warm to us, but the phase change does not. So you have to think about this in terms of the energy flowing into or out of a system. Right. Now, keep this in mind. We had this concept back in semester 1. So there is a law of conservation of energy that's very similar to the law of conservation of matter, right? So energy is going to be, this conservation of matter, it's observed along with conservation of matter. Neither one of these, energy or matter, are created or destroyed, but conserved, right? What you put into the system is going to come out of the system. Remember, balancing equations in matter, left side of the equation, right side of the equation had to be balanced, right? So total mass, total energy, they remain constant. You're just moving it around. Okay? All right, so knowing that, let's look at the actual equation for heat. So here it is. So it's Q, that's our energy, equals M, which is mass of the sample in grams, delta T. Delta is a Greek letter, right? That simply means to subtract. And it's usually your final temperature minus the initial degrees Celsius. So I think mass and temperature look at least a little familiar to you. It's the CP that is different. Now you might see symbols for S or C. Other teachers might use these. I was trained with CP, and I like to keep it this way because I think S and C get a little confusing for like seconds or calorie, things like that. So your textbook might use S or C, other teachers might. I am sticking with CP because I think it's a good, like it stands out for you as something different, right? So that CP is what we call specific heat. So every substance that will deal with for this unit will have a specific heat that we need to use in order to calculate heat flow, right? So this is the amount of heat needed to raise the temperature of a gram of a pure substance by 1 degree Celsius. That's a heavy definition, right? There's a lot of units that are involved. In fact, every unit up here, right? joule for energy, gram for mass, degrees Celsius for temperature change. So that is going to help us to cancel out different units when we solve for different letters of the equation as well. Because we don't just have to solve for heat flow. I can ask you to solve for other letters. But just to give you an idea of what this specific heat means, if you take a look at this chart, right? So you can see things like air, you have water, and you have some metals down here, you have carbon in the middle. Check out these numbers, right? Look at water. Look how high that specific heat is compared to metals. So if you think of like boiling water for pasta, right? The water takes a while to heat up, right? It takes at least a good 5 minutes or so for that water to boil and be used for cooking the pasta. So that specific heat, the energy to raise a gram of water by just 1 degree, takes a lot of energy, as opposed to the metal pot or pan that you are using to heat that water. The water's in when you're heating it up, right? So metals generally have a low specific heat. Your metal pots and pans tend to heat up quickly, right? They're hotter to the touch compared to the water that's on the inside. So their specific heats are relatively low.